Hello, guys. This is my first time trying this recording, and my handwriting isn't the best, so please forgive me. But I'm going to go over some related rates problems with you guys. So let me get started with a few examples. Okay, so I'm going to go over these first three problems in this on this sheet here. So let me get annotated. Okay, perfect. So when it comes to related rates, I generally try and break it down into 4 steps. Okay, one, determine if I could write, determine variables. Okay, first you need to determine your variables. 2, determine formula. 3, implicitly differentiate that formula. And then 4, plug in and solve for unknown variables. Okay, so those are your 4 steps, basically. Determine your variables, determine formula, differentiate the formula, implicitly differentiate, and then plug in with the variables you determine from step 1, and you'll be able to find the answer most of the time. There we go. Okay, so let's start with number 1. Okay, so we have a 25-foot ladder, okay, against a wall. We know the ladder is 25 feet. Always, it doesn't matter where on the wall this ladder is positioned, it's always going to be 25 feet, right? And the question's asking when the bottom of the ladder is 7 feet away, right? Okay, but the bottom of the ladder is not always 7 feet away. So first, we've kind of determined, I'm going to call this Z. It's 25 feet. We'll call the 7x, and it's when x equals 7 feet. We'll call this value on the wall y, right? Vertical being y, x is 7 because it's horizontal. Again, excuse my bad writing. First time I'm trying something like this. So, and also it's saying the ladder is slipping down the wall at a rate of 1 foot a minute, right? So it's slipping down the wall, which is your y value, right? So your dy dt, right, because it's over time, it's a rate, is equal to -1 foot per minute. Okay. So it's -1 because it's slipping down the wall. That's why it's going in a negative direction. Okay, so we've determined our variables, right? So that's the first step. Second step, determine formula, right? The easiest way when you have a right triangle to just come up with a formula, x squared plus, let me erase that real quick. X squared plus y squared equals z squared. Okay, so we know that x and y is going to change as the ladder slides down the wall, right? Because as the ladder slides down the wall, y gets smaller and x will get bigger. But we always know that z is equal to 25, right? So actually the formula becomes x squared plus y squared equals 25 squared. And if you plug that into your calculator, you get a final equation of x squared plus y squared equals 625. Okay. I'm just going to make that clearer. Okay, so x squared plus y squared equals 625 is our final equation. We've done step 2, right? So now we have to implicitly differentiate that formula. Right? Do the same thing to both sides of the equation. I'm going to invest in a better stylus. This is the one I had at home. Okay, so that becomes 2x, right? Because derivative of x squared is 2x. But because it's with respect to t, you have to follow the chain rule, and what's remaining is dx dt, right? When you look over here, this d over dt means differentiate with respect to t, right? Most of the time what you've done is differentiate with respect to x, which would be d over dx. But because we're looking at rates, how fast something's going, we have to differentiate with respect to t, right? So going back to this, for the same reasons, you get 2y dy dt, right? Because y differentiated with respect to t using chain rule, and 625 differentiated is going to be 0, right? Because it's just a constant. So you differentiate it with respect to any variable, it becomes 0. Okay, so we already know we have 4 unknowns here. We have x dx dt, y dy dt. We already have y here. We have when x is equal to 7. Oh, and we have to find one more, right? So the question's asking, how fast is the bottom of the ladder slipping along the ground? Well, the ground is x, right? Along the ground. That's x. So we want dx. Let me just, I'm just going to go into the next problem space. We want dx dt, right? We do not have that. But we can get, we also need y, right? But we do have this equation x squared plus y squared equals z squared, right? or x squared plus y squared equals 25 squared, or 625. So basically we can plug in x, which is 7, to find our y value. So let's just do that. So let me just write the equation real quick. 625. And you get x is 7 squared plus y squared equals 625. And you get y squared equals 576, because you get 625 minus 49. And then y equals 24 feet. Remember to include your units. I'm not doing. So I should be putting units in each of what I write. But we do know y would be 24 feet because that's the units we've been using. So now we can plug in, we can do our last step, plug into the final equation, right? So going down here, 2x is 7. We want to know dx dt. We do not have that. Plus you know what? I'm going to be the change I want to see in the world. Okay. I'm going to put the units in. 7 feet dx dt plus 2 times, so we know our y from here, we got 24 feet. And then dy dt is all the way back given, right? So it's slipping down the wall at a rate of 1 foot a minute. I did not mean to do that. Negative 1 foot a minute equals 0. Okay. So we get 14 feet dx dt minus 48. When you combine units, you see both feet are in the numerator and the minutes in the denominator. So you get feet. I can just see all of you making fun of me when I next see you after you watch this video for me struggling with a stylus. Okay, so you get 14 feet dx dt minus 48 feet squared per minute equals 0. And then when you, let's see, okay. Fortunately, I write pretty big. Okay, from here, you get dx dt equals 48 feet squared per minute over don't know what's going on. 14 feet. One of the feet's cancel. And from there, I'm just going to write this over here. You get, putting it into the calculator, 48 over 14 is 3.43 feet per minute. Notice that it is positive, so that means x is getting bigger, which would make sense as y gets smaller, right? As the ladder slips down the wall, the ladder is going to slide along the ground, and the distance between the ladder and the where the ground and the wall meet is going to get bigger, so that makes sense. We get a positive 3.43 feet per minute. So that is how fast the bottom of the ladder is slipping along the ground. I'm just going to clear everything. So the answer is, let's see. The bottom of the ladder oh my. Is slipping 3.43 feet per minute. I'm sorry about this. Bottom of the ladder is slipping 3.43 feet per minute when one ladder is 7 feet away from wall. And that's the answer. Okay, you know what? So I'm going to clear that. We'll go on to the next one. I am going to try using my mouse because maybe that might be a bit easier than using a stylus. I'll give you 2 seconds. Okay. Okay, so second one. I'm going to get out of this, annotate again. Okay. Okay, again, next related rate problem. So 4 steps, right? First step, determine known variables, right? We got this sphere. I'm gonna try and draw a sphere. That's meant to be a 3D depiction of a sphere. Obviously not the best, but we all know my drawing is not great at this point. Okay, Luckily, they've already done step 2 for you. They've given you the formula for volume of a sphere. Okay, so what do we know? We know that snowball's melting at 4 cubic centimeters an hour. So the volume is changing, right? And because it's melting, it's decreasing. So it's a negative. Okay, so negative 4 pi cubic centimeters. Remember to put the units. Okay. Cubic centimeters means centimeters cubed. A 3 there, third power. Per hour. I almost forgot to put that. Okay, so how fast is the diameter changing when the diameter is 20, right? So when diameter, just because we're already using D quite a bit, I'm going to silence my phone. Okay, so when diameter is 20 centimeters, you might be thinking, wait, diameter's not in the formula, right? Well, we know that this is equal to 2r, right? Diameter is just twice the radius. So radius, when the radius is 10 centimeters, we can just convert it right there. Okay. So we've determined our known variables and we have determined our formula. So let's differentiate this formula, right? So okay. Those are meant to be fancy D's. You use those fancy D's when you do differentials, or at least you'll see a lot of people using that. Okay. That is a terrible parentheses. I'm glad I moved to the mouse. Okay, so you get, right, for volume, this is easy, you know, if you differentiate V, you just get 1, but you have to use chain rule. And so you're left with a dV dt, right? Because it's with respect to volume, not with, or it's because we're differentiating with respect to time, not to volume. 4/3 pi is a constant. You have to remember pi is a constant. It's equal to 3.14. It's not a variable, right? So multiplied pi over r, or pi times r cubed. Or wait, I'm not listening to my advice. Pi is a constant. Okay, so dv dt equals 4/3 pi times r to the third, right? Relatively easy, 3r squared. And then because of chain rule, we're differentiating with respect to t, and this is r, so we have to add the term dr dt. You can get rid of threes here. dV dt equals 4 pi r squared dr dt. Okay, so we've differentiated, right? We did our third step, right? First step, again, determine known variables, which we did up at the top here. Second, figure out your formula that you need to use, which we have determined this formula, or well, it was already given to us. Third, implicitly differentiate the formula, and we have done that. Now we just plug in, right? We already have our r, right? We have our dv over dt, and we want how fast is diameter changing, and we can get that by knowing how fast the radius is changing, just because diameter is just double the radius. So we can plug in, right? dv dt, negative 4 pi centimeters cubed hour. Just make sure doing this right. Okay, equals 4 pi r. Well, actually, I need to plug in for r. Ten centimeters squared dr dt. I am going to rewrite that. Hopefully it's readable. Okay, so that's the formula there. So now we just solve for dr dt, right? So we get negative 4 pi centimeters cubed per hour. Okay. And then dividing the other side over, we get ten centimeters squared equals dr dt, right? And then simplifying, right? We can get rid of the 4 pi's, right? We can actually get rid of the 2 centimeters, the centimeters squared, and that cancels out with 2 of the 3 up here. So we do get negative 1, 10 squared is 100. Centimeters per hour. So I shouldn't have. The squared's still there, right? Really just the centimeters cancels out with the centimeters up here. But yeah, 10 squared is 100. But you have to remember, dr dt is the change in radius, right? So change in radius, right? Negative 1 over 100, negative 0.01 centimeter per hour. Okay, and from there, the change in radius is going to be half the change in diameter. So in order to get change in diameter, right, we need to double it. So the answer is going to be negative 0.02 centimeter per hour. Okay. And so that's the answer. So let me just write this. The diameter is changing diameter is changing negative 0.002, 0.02. Notice I put changing negative 0.02. If I put decreasing negative 0.02, that'd be incorrect, right? Because it'd be decreasing a positive amount, right? So we need to, if you do put in, it's a negative number here, make sure to write changing or something like that. If you do, but you can just put decreasing or increasing. That way you don't have to worry about the sign, right? Because increasing implies a positive change, decreasing implies a negative change, right? Diameter's changing negative 0.02 centimeters per hour when so was it when the diameter is 20 centimeters. Okay, remember to put when the diameter is 20 centimeters in your answer, because that's what the question's asking. How fast is the diameter changing? The diameter is changing negative 0.02 centimeters per hour when diameter is 20 centimeters. Okay, so on to the last one. This is the last one. This is actually the easiest one. Okay, so radius of a circle is decreasing at a rate of 2.6 feet per second. Find the rate of change of the circumference at the instant the radius is a length of 8 feet. Okay, so let me do my best impression of drawing a circle, right? Okay, there's the radius. So, radius is decreasing, dr dt, right? Radius over time is decreasing, so it's negative 2.6. Feet per second. Okay, and so we need, what else is given to us? When r equals 8 feet. Okay, we want rate of change of circumference. We'll call that c, right? We'll call circumference c. Makes sense. We want to know that. Okay, so what's the circumference equal to? We'll call circumference c equal to 2 pi r. Okay, now we want to differentiate. We've determined our variables. So that's step 1. Step 2, determine the formula. Determine that. Now implicitly differentiate for step 3. Luckily, this is one's more simple than the others. So you get dc dt equals 2 pi come out in front, and then it's just a lone r. So you just get dr dt. Okay, and so it's asking for dc dt, right? So we just have to plug in, right? We already know 2 and pi, and we already know r is negative 2.6 feet per second. So simple enough to just plug in. I'm definitely getting a good stylus as soon as this is over. As soon as I stop recording here. 2 pi dr dt negative 2.6 feet per second. I'm very surprised that one of my cats has not started yowling at this point. Okay, and then from there, you just multiply them all together. .6 times 2 is 5.2. And then if you multiply that by pi, you can either have it as negative 5.2 pi. You can either have it as negative 5.2 pi, or calculate it out. You get negative 16.34 feet per second. Okay, so that's your answer, right? Because it's negative, circumference is decreasing. So their circumference is a long word. And because I'm going to write is decreasing, I'm going to put positive value. 0.34 feet per second. When radius is when r equals 8 feet. Now, actually, for this problem, you don't really need this because circumference is already directly related to radius. It's not related to any other variable. So it doesn't matter what the radius is. If the radius is 16 feet or 5 feet, if the radius is decreasing by 2.6 feet per second, the circumference is just 2 times pi times that value. So it's always going to be decreasing 16.34 feet per second. So you don't even, for this one, because it's not dependent on any other variables, this is always going to be the answer in this case, and you don't need to put when r equals 8 feet. But yeah, that's it. I'm going to end recording. Hopefully this wasn't ridiculously long. Hopefully I didn't forget anything. And thanks for watching.